Hello, we introduced Lorentz transformation last time, and today we want to talk about the implications of Lorentz transformation in the measurement of lengths, in particular lifetimes. By lifetime, we mean the difference between two times at some point in time. One is someone is born, and at another time he or she dies, and we want to talk about how this lifetime is different for two different observers which are moving with respect to each other. This is called time dilation. As the title suggests, we will note that time dilates between the two observers. But before that, let's think of a clock uh, which is held by an observer, and this observer could be moving with respect to the clock or not moving. Either way, it measures, there's two measurements, Z1, T1, and Z2, T2. At the first event, someone is born, and the second event, the same person dies. And lifetime will be defined as delta T is equal to T2 minus T1. So that's going to be lifetime. And that's the quantity we are interested in. How does the lifetime measured by one observer compare with the lifetime measured by another observer? This process requires us to discuss what is delta Z, at what positions were these two events measured, and delta Z is in general Z2 minus Z1. But if we think of a clock held by an observer, and if the observer is holding on to the clock, is at rest, and that's surely going to be 0. So it's equal to 0 in the rest frame. The rest frame of clock. And it need not be equal to 0. It's not equal to 0 in a moving frame. So that's sort of a requirement for measurement of lifetime, that if you're measuring lifetime, it has to be measured at the same time. That means to say it's the same clock that is measuring the two events we are talking about. With that prescription for measuring time, we go to Lorentz transformation. Lorentz transformation tells us delta Z prime, C delta T prime, written in as a matrix relation. We have gamma, beta gamma, beta gamma, and gamma. And on the right hand side, we have delta Z and C times delta T. We have to now specify which observer is at rest and which one is moving. Let us say delta T here is the lifetime measured by rest frame. Right? That means to say this observer is at rest with respect to the object whose life we are measuring. And based on that prescription, we immediately require that delta Z has to be equal to 0. Right? Delta T prime here is lifetime measured by the moving frame. And in general, delta z prime can be anything. We don't specify anything, and we won't, it's a spectator here, and it doesn't play an important role in this derivation. With this much, we can immediately write down that c times delta t prime is equal to, as a beta term multiplies delta z, but that's 0. So we immediately have gamma times c delta t. C cancels out, and we have the lifetime measured by a moving frame is gamma times the lifetime measured in the rest frame. And since gamma is always greater than 1, time actually dilates, right? Opposite to what we have for uh, uh, for length. And that's all for now. Thank you.